So, Frank, I don't need to introduce you, plus minus everyone knows you, but I'm really curious, you started with philosophy and physics. What led you to trees?
My family has a carpentry and a sawmill since 125 years, so I was used working with wood from early on, as a child already. And I started working as a carpenter, but I realized, oh, that's not my business. And I was always interested in physics and philosophy because they come very close together, these two topics. And so I started studying physics, philosophy and history at the university. Then I first started working for a nuclear research facility, basically for nuclear power management. And after a year I realized, no, I want to use physics for something good. I switched back and I got a request from an institute for botany near Stuttgart, where they were looking for someone checking an idea how to use a thin needle, pressing it into wood and measuring the resistance. Their idea was, with this method, to measure the density of late wood of tree rings for reconstructing past climate. So these botanists, they were great in any kind of biology question and botany, but they had no clue about technology. And at that time, at the early 1980s, they were looking for someone who was able to deal with computers. And so the Heidelberg University, where I studied, if they could send someone who is interested in wood and would like to use physics in wood. And so they asked me and said, hey Frank, you work as a carpenter and you studied physics, so probably are you interested? And I said, yes, that's a good idea. So I moved from Heidelberg to Stuttgart and I lived there and I worked in that institute for dendrochronology, tree ring analysis. And the goal was using this needle, basically pressing it into wood, measuring the late wood density of tree rings for reconstructing past climate. As a side effect, we found out we can see decay in the wood. And then at the end of my study, I realized this may be an option to work in a private company.
This is start of resistography.
And that was the start of the resistograph, so I didn't really invent the idea. There were many people that contributed to the idea. My lucky position was that I was the first to make a machine really running and showing that it really works. So several people contributed and had good ideas, but no one of them had been able to make a machine that really works, because always something was missing. And fortunately, in that Institute of Botany, I had good help from all people knowing everything about wood. And from my background, physics, I knew a lot about electronics and computer. And then we brought everything together. And the machine at the end showed we were able to determine the tree ring width of trees instantly, within a minute after drilling. And having this as a base for climate studies, that worked fine. And as a side effect, as I mentioned, we were able to see decay in trees, and so I thought, hey, that might be the base of a company inspecting trees. And that's why I started doing this as a company. I started RINNTECH in summer 1988.
And can you summarize how the company works now and what's the portfolio?
I want to mention that when I would have known what will come to me over these many years, at the beginning I wouldn't have done it. Because I have not been aware about the problematic aspects of these diagnostic technologies in the various areas. Today we are a company with about 10 people, and we are still focusing mainly on research. That means our main income from the early beginning is from selling machines for tree ring analysis to universities. So dendroclimatic studies, geomorphology, climate reconstructions, that's still our biggest income. One part is then tree inspection, and the other part is timber inspection. Inspection of historical buildings, timber structures of bridges, timber structures of modern sports halls, for example. So we are using the technology that came from the university in various different areas, practical. On the one side, at the trees, standing trees in urban areas and in forests, and then timber in buildings, in structures. So we have basically 3 markets, which is one and the biggest by far still, tree ring analysis, climatology, making computer software for climatology, time series analysis, what is really fun, a lot of complex mathematics, then tree inspection and then timber inspection. These are the 3 areas.
How do you approach the development of new diagnostic technologies, and mainly for arboriculture, if I may ask you?
Yeah.
And what challenges do we face in that area?
Oh, we face many challenges, but I want to say, because we can always easily complain about problems. But when I look back, when I first started drilling trees in 1986, so nearly 40 years ago, arboriculture was on a much lower level than it is today. In many countries, the quality of arboricultural work really lifted up. It is much better now than it was at that time. And I remember well, when I first came out with the first mobile machine for inspecting trees, most people asked me, please give a reason to cut down the tree. And that really changed. In the last years, it's more and more, please help us preserving the tree, even though it is defective. So I think the public perception, the political, let's say, movement in this direction is really positive. So when I would like to make a bottom line now, I think arboriculture really developed much better now in all these years. And this is exactly the situation where new challenges for new technological developments come from. Just simple example, when the government decided in Germany to build more glass fiber cable, we had so many conflicting situations where the companies should make a trench, but it would destroy the trees because it would directly cut off all the roots. So we were looking for a method to find a way to detect where the big roots are. And then it took me about 5 years to develop a method. I checked many other things, that similar work on soil and mechanical connections. And finally, we found a solution to find roots even below pavements in the cities. So most of the developments of new technology comes from challenges where we have no solution yet.
Can you list for me what devices do you offer for arboriculture?
In the case for RINNTECH is basically the resistance drill, the resistograph drill, then a sonic tomography with an extension for working on the ground to detect where the major roots are, then a pulling test equipment that is called DynaTim because we developed it in the 1990s for timber structures. So originally it was made and developed for measuring the load-carrying capacity of wooden bridges, for example, or wooden roofs. And then over the years when we applied it, at one situation there was an arborist seeing us and said, hey, we would like to apply this on a tree. And then we extended to apply these pulling test equipment on trees. These 3 devices for tree inspection, and then inspections in the laboratory. So we have several kinds of laboratory analysis, often included with a big microscope. Systems working on stem discs or increment cores that universities need for doing both tree ring analysis and density analysis, because the radial density profile much better reflects past climate and impacts on the tree than just the ring width. So it's a set of 5, 6 different kind of devices, part of it only for universities, and the 3 that I mentioned for practical application on trees. And we started developing apps, yeah, that's right. So we did already, I think it was, the first was 1988 already, Windows programs in this case, and now since a few years we even offer apps in the app stores for smartphones and mobile application. For example, wind load analysis or any kind of measurement, reconstruction of an internal defect in the tree and determining, for example, what is the strength loss due to the defect. These are apps, and we are now bringing a lot of apps that we originally made for the desktop computer now to be applied on mobile phones, for example. Yeah.
To Today we are at the Baum und Boden seminar in Jena, and you showed here a very interesting presentation about the wind load analysis. Can you summarize the main points for us?
Yeah, I think it's quite simple. When we want to determine the wind load of a tree in absolute numbers, so in kilonewton meter down there at the stem base, both torsional and bending moments, we will fail because the boundary conditions in the urban environment are so difficult that I think it is impossible to calculate the wind load at a reasonable precision because the uncertainties about wind speed, the wind profile, climate impacts and all the other things are so big that the variation in the estimated result, I think it is definitely more than plus minus 100%. That means the imprecision is so high that I think we should avoid these kinds of measurements. It is no problem, for example, to find out what is the change in wind load by reduction pruning, for example, or by geometrical changes of the shape of a crown. So relative changes of wind load, I think that's quite easy to determine, and that works well with a sufficient precision, because when we do relative analysis of changes, then all the difficult values kick out of the equations. And this is why I think that we should focus on methods where we need a relative change in wind load and not the absolute number.
And this is how you approach it with devices you use?
This is how we approach it with, yes, exactly. So we try to enhance the pulling test. The pulling test is, for several applications, I think the only method that is suitable, but the pulling test analysis using the absolute wind speed and the wind load is difficult because it is very limited in its precision because of all these boundary conditions that I just mentioned. So this is why for several years we worked on a way to do pulling tests and to do the analysis that is independent from the wind load assessment. So that means a relative analysis. We call it allometric self-referencing, which means that we try to compare the tree with itself, because the stem of a tree is the response of the tree to the wind load. So this gives us the reference where the wind load information is stored in, because the radial growth of the stem is a response of the tree to the wind load. As long as the tree is standing up, it's a proof that it was sufficient, otherwise the tree would have been blown over already. That means we try to establish methods that allow us to evaluate both the breaking strength or the breaking safety of the tree as well as the uprooting safety by comparing the measurement values with the intact stem. And by doing these relative analysis, again, a lot of the complex and difficult values like strength properties of wood or wind speed kick out of the equations, and by self-referencing, that means by comparing the current tree with the previous situation of the same tree, we get results that may be able to replace all the other methods that are using absolute values. So our goal is to achieve a combination of methods that allows us to determine the breaking and uprooting safety of trees without having the need to determine the absolute strength of wood and the absolute wind load to the tree, just by comparing relative changes over time. Basically, the total wind load of a tree is largely proportional to the total height of the tree to the power of 3. The cross-sectional load carrying capacity is proportional to the diameter to the power of 3, and this is why the trees keep height over diameter ratio constant as long as they can, until they reach the maximum height and don't grow in height anymore. And this allows us to determine the safety of a tree later on by comparing it with these basic implemented safety features.
I can imagine this comparison for the breaking resistance, but how you approach it for the uprooting resistance?
That's a good question, and I was struggling with that topic as well. Fortunately, there's some research out showing load carrying capacity of the stem is usually in the same magnitude of order as the uprooting or anchor moment in the ground. What makes sense? Because it would not make sense for the tree to have a weak stem and a strong root, and vice versa. So the strength of the stem and the safety of the stem against bending is usually similar to the uprooting safety of the whole tree. So when we are measuring the inclination of a tree under load and we compare it with the bending of the stem under load, we can compare if the root is stronger than the stem or not. For this comparison, we don't need to assess the wind load. We just compare the strength of the root with the strength of the stem. And when the root is significantly stronger than the stem, although the stem is intact, that means the root is automatically sufficiently safe. When the stem itself is highly rotten and defective, then we can't do this comparison anymore.
Do you had any funny, surprising moments when the readings from your devices completely changed your view at the trees?
Oh yeah, several times. I remember we had many old trees. We inspected a lot of so-called natural monuments, and sometimes we had completely stupid results, and I was sitting there at the tree for hours and I couldn't figure out. And sometimes it was the fact that this tree was steel bolted 50 years ago, so there were steel bars in the tree, and it drove me nuts until I realized that the values of the steel that was still implemented in the tree and well connected completely destroyed the information of the sonic tomography machine. And when you don't know that, you don't see any signs at the stem, it drove me crazy at the tree. I didn't find a solution. I thought the machine was wrong, and it took me hours to realize that obviously there were steel bars in the tree. Yes, and that was the case.
Okay, you are in contact with many people using your devices. What are maybe the biggest misconceptions?
Often people tend to use technology that they don't understand, and they inspect trees that they don't understand. Most of the technology that we provide, first of all, you need to understand trees and the wood anatomy. Without understanding biomechanics and wood anatomy, you don't know where to apply which machine in which way. So unfortunately, I would say the vast majority of reports that I get for cross-checking are just wrong. People drill on the wrong spot, in the wrong direction, are not able to interpret the profiles correctly, and the same happens with sonic tomography. And a lot of these misconceptions come from wrong advice, from allegedly competent people. So, for example, it was several times published and presented on conferences that you should drill between the buttresses. And this is fundamentally wrong. All the mature old trees in the urban environment, we should drill into the buttress and not between the buttress, because between the buttress, first of all, biomechanically it makes no sense because it's not necessary. And second, when you drill between the buttresses, you often have included bark and the profile doesn't show wood. And we lost a huge number of trees because people drilled between the buttresses, didn't see a nice profile, cut the tree down and thought, oh shit, it was intact. The other aspect with sonic tomography, unfortunately there was even a professorial advice, please put the sensors as deep as possible because we want to know if there is decay coming from the ground. But then included bark again between the buttresses inhibit the sonic waves to go through, and the sonic tomography picture looks decayed, but it is intact because the included bark blocks the sonic waves. So the machine was correct, it was just applied wrongly. It would have been nice when it would have been possible to make sure you need to do some education, you need to understand wood anatomy, biomechanics, and then you should be able to buy a machine and then to apply. But you need, again, in addition, training in how to use the devices and then how to do the analysis. And I think often the investment in education, learning, reading is more expensive than the machine. And I think a lot of people are not aware about that.
So if you should advise some young arborist wanting to use these devices, what would be your directioning?
I think it is important first to work with trees, to get a feeling with trees. Climbing is a very good preparation. I realized when I often have contacts to climbers that, for example, had an accident or couldn't climb anymore and then started doing diagnostic work. And these guys have often been very clever because they understood trees by mechanical climbing. Yeah? You know, you climb up, you understand, and you get a feeling for mechanical loading. So this seems to be a very good preparation. One problem with good climbers often is that they have so much fun being in the trees that they stop learning and reading. And they often struggle when they then come back to the seminars, and after 2 or 3 hours they're just like, oh gosh, is it boring? And they have the knowledge that is good base for doing diagnostic work, but often they they missed to go on training continuously to educate yourself. And this is one of the reasons why I really think it's good what the ISA established in the United States. You get a certificate, certified arborist or whatever, but you have to provide continuing education units that forces you to go to courses, to learn and to go on and not to just stand still.
Do you have any generic message for the industry of arboriculture you would like to convey?
Don't believe what allegedly competent people just tell you, but challenge everything. Read and educate yourself.
Thank you very much.
Thank you.